Thank you, Julian, for the invitation. Thanks for the organizers for giving me the opportunity to speak here. So I should maybe say that this is my very first project on geometric flows, and so I'm quite happy to tell you what we did. And it is in collaboration with Malte, Kampschulte, and Joonas Niinikoski, who already before worked on volume preserving mean curvature flow, which is somehow the background for this research here. And the subject is actually, here is sort of the setting. So maybe I should first take this one. So we have like a fluid droplet. This is the situation. There's a fluid. And then we have surface tension. And then we want to understand the evolution of these two. So this is the situation. So you have a fluid velocity and you have a geometry. And then the forces of the fluids are in equilibrium with the curvature at the boundary. So here is like the setting. So this is the PDE version here somehow. So you have like a union of time-changing domains. So you have like this time slices, if you wish, and they change. This is the time-changing domain. This is the droplet, which is changing. Then we took the simplest possible fluid equation. So here we assume that in this domain we have satisfied the Stokes law, where U here is the fluid velocity as set, and P is the pressure. So this is the divergence free constant. So this is vector valued velocity field. And at the boundary, the forces of the fluid are equal to the mean curvature tensor. And the evolution of the fluid, so this is like, if you wish, PDE point of view, double boundary conditions. So the change of the domain is also given by the fluid velocity, or if you wish, the fluid has to follow the evolution of the domain. So these are the situation. This is the situation here. So here is a bit of a notation. So we have like a viscosity constant, strictly positive. The fluid forces are more or less what you get by integration by parts here. If you want to get a weak formulation, so you get the pressure and the viscous forces. And you have like the symmetric gradient here, which is due to sort of rotation invariance of the system you want to have it. This is the normal, the outer normal of the domain, the scalar mean curvature, and Vt is the normal velocity of the boundary. So this is the... Okay, here's the picture again. And so this is a simplified model actually of a droplet of an incompressible high viscosity fluid in vacuum driven by surface tension. And so what is maybe important is that these equations are invariant under rigid transformations. So in this sense, they're not unique. You can always rotate this. And balls are stationary sets. So if you have a fixed round droplet, then this is a stationary set. And you can, but inside you can maybe rotate. So what is important is that these solutions, you don't really care about the tangential flow. So in tangential, you can do what you want. So the fluid can rotate in tangential direction as much as you want. And in particular, you have like a stress-free configuration in tangential direction. So the forces in tangential directions are zero. These are free. So this is the geometric description. And here's the background. So this is a very well-studied problem. And this is including for Navier-Stokes fluid. So you can study the Navier-Stokes fluid with surface tension. You can study several fluids which are like separated by a surface. And there are lots of wonderful works here. You have instant analyticity, for instance. You can have a short time existence already for Navier-Stokes, for unsteady Navier-Stokes. And in particular, in the planar case, which we also will consider in the future, you can actually write it as a complex ordinary differential equation if you wish, and you could study this. What is sort of the point of our work is that in general, these studies are based on the Lagrangian viewpoint. We also do this to some extent, but sort of the construction usually are based sort of that you sort of say, okay, you locally have a graph, you sort of write in a Lagrangian description your coordinate system of your surface, and you study it in this way. And sort of our work is to study it as a geometric evolution, so to take the Eulerian point of view. This was sort of our motivation, how we started here. Yeah? And it's somehow motivated, I mean, it relates to like Niinikoski, Joonas Niinikoski, who was my postdoc in Prague, who did sort of work on this volume-preserving mean curvature flow together with Eulerian. So we sort of took their setting as a, wanted to see how it works when you have a fluid inside, how this relates maybe. And so this means in particular that we wanted to look for energies. We wanted to see whether there are certain geometric quantities that are preserved. This was our point of view. And behind this evolution, there is a functional. So you have a gradient flow structure actually for this problem. In particular, you sort of, if you this is the weak formulation, so you see that if you sort of have a divergence-free vector field, then if you do the integration by parts, the pressure vanishes, and you see sort of that testing the equation results in the forcing that is precisely the mean curvature at the boundary acting on this field. And this from this equation, you can then sort of realize that actually you have a gradient flow on the perimeter, which is a viscosity that is given by this Stokes energy. So this is the natural energy related to this problem. And so this question is, do we have higher order energy estimates maybe? So this was like our question here. And so this was like our aim, yeah. So we took now 2D, and so we just have Stokes, we just have 2D, so the simplest possible situation, if you wish, yeah. And we sort of thought, okay, are there energy estimates for this quantity, which is like first order, if you wish, or even second order, where this means that you actually look at the curvature squared, you have a viscosity of higher order on the velocity, or you even take the tangential derivative of the curvature, and then you would have an H3. These are Sobolev spaces in the interior for the velocity. And somehow what we took as sort of our basis of computation is that we sort of assumed that we have this uniform ball condition. So this essentially means we always do our computation in the situation when we are quite smooth. So when in every point you have like an outer ball and an inner ball, and this radius is somehow fixed. Yeah, so this is this picture. And this is somehow the basis of regularity at which we want to sort of do our analysis. Yeah? And this essentially means that you're quite smooth. Yeah? This is like for strong solutions, but as I mentioned, like the existence of strong solution, even like the fact that solutions are getting smoother instantaneously, this is known. Yeah? Sort of what is new, what was sort of our contribution here is sort of to derive like explicit estimates, Eulerian estimates for these quantities. Yeah. Okay. So here is like the limitation. So, and somehow the question is, so this is a singularity. It's a very simple setting. You just have two annuli. And so here you have these two balls, and here is like, let's say, the fluid. And then the curvature flow will push sort of inside. Yeah. And the little ball in the middle will shrink and will vanish because there's nothing inside. The fluid is just outside. And this you can sort of compute explicitly. I mean, you can essentially take the gradient of the fundamental solution, which is a harmonic function. You get the constant pressure accordingly, and then you sort of radially symmetric, so you see sort of what happens at the boundary, and you compute the curvature evolution there. And then actually you realize that when t goes to this value t0, then this curvature squared actually will explode. Yeah? So this is the little ball will be, this is the little ball, this will have like a perimeter of length L approximately, but the curvature is also like 1 over L, right? So if this is little L here, then the curvature is 1 over L, so 1 over L squared times the surface, so you still have 1 over L left. And this explodes, so essentially, in such configuration, you can sort of have also singularity. This means it cannot hold like for arbitrary situations. There's some condition is sort of necessary to be able to get these higher order estimates. And somehow the question is this the only thing that can happen? Or can there be more complicated things? If you have a fluid that is blocking, right? So the fluid, of course, makes lots of trouble. It produces that you have a very weak information on the curvature a priori, yeah? Because the trace of a fluid force, if you're in H1, this is, yeah, doesn't even exist. Yeah? It's a very strange forcing. But on the other hand, it's blocking, right? It's like blocking. It cannot evolve freely. So this is sort of, and the question is how these two different things, how they interpolate somehow. Yeah? Okay, so here is like the main result. It looks pretty ugly, but it is like an estimate, right? So it's the estimate that we wanted to get. So you see here, like this is the mean curvature squared, or in 2D, this is just the curvature squared. Then you have a sign on the viscosity here, so the second order estimate in U. And then you get a lower order right-hand side. It's not really lower order, actually, because this R is actually this inner ball radius. So this is actually too high. So this is not an estimate that closes. Yeah? So you have to sort of assume that this is bounded, and then you get this. But when you push this one level up, then this is actually higher order to this quantity here, so it's still there. And so this is even more complicated. Yeah, it looks, it has this square here, so it's not one homogeneous anymore. This is also not one homogeneous because of these scaling factors here. But this is an estimate which you can close for short times. So this is the second part. So actually you can prove independence of this quantity, that you have a continuity of this inner ball radius. Yeah? And this RT is like sort of the maximal radius such that you have an inner and outer ball condition. This is sort of what defines this RT. And this you can show that it's actually continuous with respect to time. Okay, so this is the main result. It's still 15 minutes, right? Something like that. It's until quarter past or 20 past? Okay, perfect. Okay, so here is what you would like to do in principle. Yeah, so this is so you want to just, there are now some T-missions, but in principle you want to differentiate this. You sort of use that the derivative of the curvature is maybe something like the tangential Laplacian normal direction, and then okay, here you get sort of something like Reynolds transport theorem. This is already an ugly error term. And then here, this you use sort of as, you use that the H is equal to the forcing of the fluid, so this becomes like a test function for the fluid equation. And then hopefully in the end, you sort of reach with the viscosity, let's say at least in tangential direction of the velocity with the right sign, plus error terms. So this is sort of, this is the heuristics why there is, let's say, a chance. Yeah? And how it really looks like is a bit more ugly. And so here I will do a bit of notation. So we also use the sign distance function. It was already introduced, right? So we use this inner ball condition, and then we know that we have this fiber, so we can like extend our normal as the gradient of the sign distance function, and also the tangential by just projecting it to the tangential where it was. Yeah. So this means we have like a tangential field and a normal field, and then you have like other quantities. You can, in particular, you get like the curvature in some sense as your divergence of the normal. Yeah? So this is computations which you can do on this tubular neighborhood, and then what is sort of okay? This is like the analysis. This was maybe part of the hard work. So essentially, you want to show that your error terms are lower order terms, this means you need to be able to estimate, let's say, a velocity by a gradient, something like a Poincaré or a Korn Poincaré actually here, because there's a symmetric gradient. And all of these estimates, you have to make them somehow uniform in your geometry, right? You need uniform bounds, even so your domain is changing all the time. So here again, you fix like this radius. This is sort of the constant that you fix, and for all domains sort of satisfy this inner ball radius, maybe also some perimeter constraint. Yes, here it is. They satisfy these inequalities. And for this, we had to develop quite a number of analyses. I think we did it essentially using Bogovsky operators and dual norm formulas. And yeah, so up to now, we don't know that whether these constants are optimals. In some cases, we know they are optimal. So if you make thin domains that are very long, actually you get precisely these scalings. And then you can also uniformly prove interpolations. This is 2D interpolations, of course, of V in L infinity or in H1 by lower order. So this is a necessary part that we need in order to sort of be able to close the estimate, so that we show that, what you think is lower order really is lower order. Okay, and so here is now how this energy estimate then really looks like. So, I mean, you start with this differentiation of the term that you want to have. You get something like the tangential Laplacian here. You get the flow. So this is the tangential Laplacian, right? You get something like Reynolds transport for the surface, and sort of here you use the fact actually. So this is the the estimate for the curvature. Here you can use this hidden boundary condition that actually in tangential direction you are stress free. So there is nothing blocking you for taking whatever speed you want on the tangential direction. And this actually allows you to sort of sneak in here the full Laplacian. And this is quite nice, because sort of you actually get an equation where you have here the full Laplacian squared. If you do this, so here you use the equation again. And so this is sort of if you want to prove regularity just for the Laplacian, then you usually, or let's say for the Stokes equation, then you first prove tangential regularity, then you use the equation, do manipulations, and then you get full second derivatives. Here, because of these boundary conditions, it's not necessary. You get at this level, you get directly second gradients. Of course, it's not a miracle. We will have other terms to treat, and this is actually appearing here. So if you sort of then change the Laplacian to second gradients, you get like this nice boundary term, which looks as if it is not lower order, right? So because you have on the boundary a Laplacian and a gradient, so this is a bad thing. So this high order. But what saves you here is the divergence-free condition, which allows you to sort of put this back into the domain, and sort of this is really like counting derivatives. Sort of you realize that sort of what you get here is actually only a part of this term. So it is. You can really use sort of that this term is sort of dominating this term, and in the end you get a part of information. In the interior. So this eta here is a cutoff function, and this is because when we sort of convolute this back in the domain, or we put it back, so this is a normal direction, so we can like use divergence theorem to put it back into the domain. We have to sort of extend this as a field, and we have to cut it off so that we sort of make sense out of this expression in the tubular neighborhood. Okay. It's very technical, I'm afraid. But in the end, somehow it is quite nice that sort of if you remove this term, you actually have some leftovers here, and you can actually then sort of use this inequality here, which actually shows that whatever is left over is actually not enough to control the full gradient. So this is this part here. Was your positivity part. And this is sort of enough to get it. Here is some, this is of course lower order. This comes from the using curved coordinates here. Yeah. Okay, so this is sort of the story when you want to estimate the h squared. And when you want to sort of go to one order higher, so this is like the higher order means, in this case, you want to get an evolution for the tangential derivative of the curvature squared, maybe plus some dissipation. Let's say, write it as some third derivatives of u, maybe. This is on the boundary, this is in the interior, this is the time derivative only on this. Then things are sort of similar, but even more technical. But essentially, you go through the same procedures. Yeah? However, in this case, this is sort of important. In this case, you cannot like get the full second order, the full third order immediately. And this was sort of a nice observation that in this case, actually, you can use Korn-type arguments by writing whatever you have as a symmetric gradient of something weird, and then use abstract Korn estimates for this, and this would eventually give you the full third derivative. So this was quite nice technical trick here. Yeah. Okay, so this is sort of how you close it then. I mean, once you have this second order, this higher order estimate for the curvature, you can sort of, this is like the control that you can also get. This is essentially estimating the dissipation by its boundary values. Yeah? So this is very artificial now. But somehow, when you do this brute force, you get horrible exponents here. And in the end, you actually realize that you can get a uniform control for some time. For this tangential term, and the continuity estimate, additionally, if you have the continuity of the inner ball radius, then this actually means that for some time, at least, you have a control on this inner ball radius. And yeah, this is the quantitative 1/3 Hölder continuity of this map, and this implies then the uniform continuity of the inner ball estimate, which closes the estimate. So, this is what you get, I think, when you sort of geometrically want to get explicit a priori estimates in this setting. Yeah, so the question is, I would say still, if this is giving any new insight, it's sort of a start of a quantitative theory, if you wish, in some sense. But what it would really good would be sort of to understand singularities using these maybe. Yeah, seeing what happens sort of. And there are more open questions here. Yeah, these are the follow-up questions. Sort of. Yeah, so the question is sort of the optimality. In some sense, it's optimal with respect to this picture. Yeah? So in this case, somehow is a sharp counter example to the estimates that you cannot sort of do much better, at least, in some sense. And sort of then the question is whether you can sort of push this further, because we know by other results that analyticity is available. So you could expect maybe arbitrary powers here, yeah, so that you get smoother and smoother, because we know the evolution has this property. And then, of course, the 3D case is interesting, because in this case, actually, you have then the mean curvature. This means, yeah, the geometry is maybe less connected to the, I mean, yeah, it's just a trace of the fundamental group. So, I mean, yeah, you could have like droplets in this form, right, where you have one small and one big radius. So the question is whether this is actually some kind of work in progress, that you can maybe do this method also in 3D. And then this is sort of maybe my favorite question here. How is it when we sort of include the time, because we have an evolutionary problem here? So what are sort of the higher order in time estimates? So these are something that might reveal some more properties of the flow. And yeah, and then of course the understanding of the singular points. Okay, yeah, I'm stopping a bit early. Here are some references not all I mentioned. I thank you for your attention.